In today's modern vehicles, we've seen widespread adoption of oil coolers as car manufacturers are now producing not only higher powered, but higher efficiency and turbocharged engines that generate far more heat and require much better oil cooling mechanisms than cars of the past. Hi, I'm Corey, and welcome into today's Standard Pro Training Power Hour, where we're going to discuss why cool oil matters. Now, there's a lot more at stake than we might actually think, and far more advanced systems that are now dependent not only on the correct oil, but oil that stays cool. Now, we've got a lot to cover in a very short period of time, so I'll meet you over at the bench and we'll get started. And so again, the topic today is why cool oil matters. Again, we're going to talk about several reasons why that's true. But we're also going to talk about some of the mechanisms in place to help get that oil cool, how they work, and what the breakdown looks like, why we need these oil coolers to service the vehicles that are on the road today. Whether it's an older diesel application or some of the newer platforms that are out there, whether it's an aluminum housing or whether it's something made of Zytel like we have on the 3.6 liter Pentastar applications, there are multitudes of ways to cool the oil, but there's a lot of reasons why we want to. And that's one of the things that we're going to talk about today and some of the systems that are dependent on that cool oil. First though, let's talk about the agenda, how we're going to go about discussing this topic. So in order for us to understand why cool oil matters, we really need to understand what it is that oil does. And we'll touch on this just a little bit. And then once we understand what the oil is doing or what it's meant to be doing, we're going to talk about how it works. How does the oil take care of these tasks? How does it get the capabilities that it has to do the things that the motor and other systems are expecting it to do? And speaking of those other systems, we're also going to talk about those systems that are dependent on oil cooling that are found in most modern vehicles today. And then we'll discuss what an optimal temperature looks like. What should it be? What should we be expecting if we're looking at the temperatures of our oil? And what happens when we have excessive heat above those optimal temperatures? And then we'll talk about some oil cooler operation. How does it do what it's supposed to do? How does it keep the oil cool during the process of driving down the road? So that's our agenda, and we'll get into that now by, again, talking about what does the oil do. So here's what the oil does. We all know the primary purpose of engine oil is to lubricate the internal moving components of not only the valve train, but the rotating assembly as well. The thing is, though, it's always had and served more purposes than that. And with today's modern vehicles, oil has been tasked with so much more than just maintaining the lubrication. So here's some of the other things that the oil does. It also is going to assist with sealing internally. And while the engine gaskets themselves do a great job of keeping oil and other fluids contained within, the engine oil aids in this by helping to seal from the inside, trapping contaminants and deposits that may otherwise damage the gaskets, like say the head gaskets, the valve cover gaskets, and the oil pan gaskets. But we can't forget also about things like the rear main seal, spark plug tube seals, oil feed and return lines, and there's so many other sealing points that the oil passes by with every mile driven. The oil also protects and keeps the engine clean and free from corrosion, things like carbon deposits, rust, and many other factors that can cause premature wear of internal components. Now, the problem here is when service intervals are not followed or the wrong oil is used, that's an important one, breakdown can occur rapidly, causing what we see here in the image of the right, essentially rendering the motor useless. Now, if the oil is staying cool and doing its job, along with regular routine maintenance, we would expect to see a clean and shiny valve train like we do here on the left. If, however, though, we do find that we see what's on the right, we know immediately that this probably is an engine that the oil has not been changed in a very long time. Now, in addition to all that, the engine oil also transfers heat, kind of like a heat exchanger. It draws heat away from the internal components as it's either passed by or washed across those components. This is yet another reason why the temperature of the oil is so important. As we're pulling that heat away, we increase the oil's overall temperature, and now we need to, once again, cool it down before it makes yet another pass, so that it can remain effective at not only transferring the heat, but all the other tasks it's tasked with. And keep in mind, having a well-maintained and properly operating cooling system is also critical in this step. The cooler the engine is to begin with, the less heat the oil has to transfer. But what about acting as a hydraulic fluid, using built-up pressure to control critical systems found in most cars today? Are there instances where maybe the oil pulls double duty? Well, we'll discuss that here in just a moment. But first, let's talk about how the oil does everything we've talked about so far. Now, we know what it's supposed to do, but how does it achieve all of these tasks simultaneously, all at the same time? Well, it's always going to start with a base crude oil, and then it's going to be conditioned and enhanced with additives. Now, some of them have more and some of them have less, but there are multiple additives commonly found in pretty much most motor oils on the market today. Keep in mind, this is true not only for the engine oil, but automatic transmission fluid and gear oil as well. So we might be on the topic of oil now, but the same principles and consequences we're discussing today will apply when considering both an oil or a fluid's longevity and its overall effectiveness on what we discussed before, things like the lubrication, the sealing, the protection, keeping things clean, transferring that heat. So what are some of the most common additives, those commonly found additives in most motor oils? The first and one of the most common are going to be antioxidants. These additives are going to slow oxidation, which is the primary cause of oil degradation. You got to remember, excessive heat accelerates their consumption, and once depleted, oil oxidation is going to occur rapidly, allowing for an increase of wear internally. Then we have anti-wear additives, one of the most common being zinc dithiophosphate, or ZDDP, which is a common anti-wear additive, and you can kind of think of this as a smooth sacrificial barrier between the metal surfaces, preventing the friction that causes wear. And once again, it will begin to degrade at temperatures above 300 degrees Fahrenheit, really even 250, 260, reducing its overall effectiveness and preventing metal-to-metal contact. Then we have detergents, and these additives are designed to prevent corrosion and sludge buildup. Now, as they degrade, also, the engine oil is going to thicken or become sludgy, restricting the optimal flow through the oil channels, and this can cause engine damage as well as excessive carbon deposits. It's also going to make it a lot harder for some other systems to work. Then we have dispersants, and these additives are designed to keep the engines clean by suspending contaminants within the oil. And they also degrade gradually with prolonged heat exposure, which means they'll lose their ability to control the contaminants, leaving them in the engine in the form of deposits. Now keep in mind on this one, I talked about sealing from within, helping trap those contaminants to better protect the gaskets. These are some of the things that they're trying to pull away from the metal surfaces and those gaskets, those contaminants and those deposits. Then we have viscosity index improvers, or let's call it viscosity modifiers, which are going to allow for multi-grade oils like a 1030 or a 530 as opposed to an SAE 30, which is going to give protection across climate and temperature ranges. Now, the problem is these polymers can break down at high temperatures, and that's going to lead to both oil thinning and reduced performance in maintaining the viscosity across those different temperature ranges. And another very common one that I don't have listed here would be anti-foaming agents. And pretty much every oil is going to have a version of this, and it's there and it's meant to reduce the oil and the air surface tension. Now, this is very important because without it, the oil can become, or will become, very foamy, which is drastically going to reduce its pressure and the ability to do its job properly, along with affecting a lot of other major components and their functionality in the cars that are on the road today. All right, so now that we have talked about what the oil is supposed to do and how it's supposed to get it done, let's talk about some of the systems that are now dependent on not only oil, but cool oil in most of these modern vehicles that are on the road today. And as you can see on the screen here, we can't not talk about turbochargers at this point because there's just an overwhelming amount of turbochargers on vehicles today. Whether it's a 4-cylinder, a 6-cylinder, there are just so many cars on the road with a turbocharger now, again, because these manufacturers are trying to enhance performance, but also enhance efficiency at the same time. But with the turbocharger comes an impressive need for not only oiling and lubrication, but keeping things cool with something that's rotating at thousands and thousands of RPMs every minute. The thing we have to remember here is this: whether it's a 4-cylinder, 6-cylinder, whatever application it is, These turbochargers are really at a basic level going to consist of just three major internal components that we really want to be concerned about: the turbine side wheel, the compressor side wheel, and then the bearing system that supports that turbine shaft. So the center housing rotating assembly, that main heart that goes in basically the center housing of the turbocharger. I've heard other people call it the chunk. It's got a bunch of different names, but we're talking about these three major pieces of the turbocharger that are wildly affected by the cool oil and the lubricity of the oil. Because you have to remember, these turbochargers can spin up to tens of thousands of RPMs. And just to give you an example of just how small some of these are and how important it is that these are lubricated properly, I'm going to go over to my cart here and just show you a couple different examples of what I'm talking about. So on the cart here, we have several different things displayed, but the point we want to get across here is this. One, the magnitude of just how small these components are in relation to what they're actually doing as those RPMs are going. You got to remember, turbochargers are going to operate at an extremely high speed, tens of thousands of RPMs, and they're going to get into temperature ranges exceeding well over several hundred degrees Fahrenheit. So keep in mind, we're going to talk about the optimal temperature range for oil here in a moment, but it's definitely far less than what these are getting heated up to during operation. So our goal, again, remember, oil is a heat transfer. We want oil to pass through and by these components and try to pull some of that heat away. Even if it's a severe amount of heat in comparison to what the rest of the motor is running at or what the oil is at, the cooler the oil, the more heat we can draw away from these turbochargers. That way they're protected a little bit better. But here's some of the things that happen whenever we have poor lubrication or poor oiling of a turbocharger. If things like the viscosity modifiers have broken down, those polymers have broken down to where we don't have our full range of viscosity. If we have too low viscosity, we could have a reduced film strength. Thin oil may not form a sufficient hydrodynamic film, leading to more metal-to-metal contact surfaces on the turbine's shaft or the bearings, and it can increase, overall wear in the bearing, causing damage there, or scoring, or even an imbalance in the shaft itself. I'm sure we've all seen the in-play of a worn-out turbo before. Oftentimes, that is related to oiling in that shaft. And then, of course, if we have too high of viscosity, say the oil's too thick, and this is more so a case of someone using the wrong oil, we could end up restricting the flow. And if we have a restriction in the flow, that thick oil may not circulate quickly enough, especially during cold starts, which is going to lead to a severe delay in lubrication of that center housing. It's also going to allow for heat to build up, and that slow oil flow can result in overheating of the turbine bearings very easily. And then in addition to that, too high of viscosity, too thick of oil, it can leave a lot more deposits. It's more prone to thermal breakdown at high temperatures. So those deposits that it's trying to trap and contain can end up being left either on the components, the moving assembly itself, or leaving deposits blocking the oil passages. Either way, we can't have that when we have a turbocharger spooling up at tens of thousands of RPMs. And we also have to consider certain things too with the oil when it comes to turbocharger, especially with those oil feed lines. So, let's say we did have the proper oil, it was staying cool, but we have a line like this where at first glance, it just looks used, it looks a little worn. But on this example, we took this off of a vehicle that was severely under-oiling the turbocharger, and we had a very small leak. Took us a good little while to find it, but we found it in the braided portion of the hose, and once we took it off, you can see it takes very little effort to collapse that hose. It's actually split. We have our oil coming out of this side, but because of the split, we didn't have a huge leak. We had a small leak because it was mostly restricted. And so we got to be very careful when we're looking at not only the coolness of the oil and the quality of the oil, but is the oil making its way to the turbocharger? If we have the oil doing what it's supposed to do, staying cool, we shouldn't have deposits building up. We shouldn't have any metal-to-metal contact or wear out of the bearing. But none of that matters if we can't get the oil to the turbocharger. So it's always important when we're looking at turbocharger damage or, any type of oiling issue with a turbocharger, check these lines to make sure we don't have a restriction or a leak. That alone can be the death of a turbocharger, and we may even have the correct oil at the right temperature, but it won't matter because we're not feeding it to the turbocharger. So with all that said, let's think about some of the more common complaints with turbo damage in relation to oil. We could have a seized or a sluggish complaint. Maybe it's seized completely, or it's just a little too tight to rotate. Oftentimes, this is going to be due to a lubrication issue or oil degradation, more commonly oil degradation, which is going to cause a high buildup of carbon in the bearing housing interior, restricting that rotation. Remember, we don't want that carbon buildup, and the more the oil degrades, the quicker that carbon can build up because we're not be able to trap those contaminants like we should. Along with that too, when we think about that hose I just talked about, insufficient or an intermittent drop in oil pressure can cause the rotor to seize as well and can introduce a lot of dirt into the lubricating oil. So it's going to cause a lot of issues if we have a restriction or a drop in oil pressure making its way to the turbo. That's why we have to check those lines. And then if we have a complaint of, say, worn or excessive clearance or something we've noticed during a diagnostic check, and we're just kind of seeing what that clearance looks like or how the wheel spins, these are going to sometimes be misdiagnosed as worn bearings. If the clearances are out of specification, the cause could actually be attributed to a lubricating problem, right? Insufficient oil, maybe dirt has gotten into the system, especially when we have hoses that will allow things in and out, or oil contamination within the coolant. So there's a couple of different things that can cause this, but with a worn or excessive clearance, again, one of the first things we need to check is the oil getting to the turbo the way that it's supposed to, being able to sufficiently oil the turbo. And so that's really just a good quick rundown of why cool oil matters in relationship to turbochargers, especially with the overwhelming amount of vehicles on the road today with turbochargers. Again, it's not just the motor anymore we're protecting. There are other systems at play that we have to consider when we think about not only the oil we use, but how long we allow it to be used, meaning service intervals. And with that, we're going to move into now another system that I know we've all been working on for years and is highly critical that we have not only good clean oil, but cool oil as well, and that's VVT systems. And with VVT, we have to remember that the viscosity of the engine oil plays a significant role in the performance and the reliability of the variable valve timing solenoids, right? So we talked about what it looks like on a turbocharger if the viscosity is too low or thin or too high and thick. Well, we have, consequences with VVT as well. If the oil is too low, if it's too thin, we may actually have it flowing too freely, reducing that hydraulic pressure required to properly actuate the VVT solenoid and the related components. Remember I asked earlier, does it act as a hydraulic fluid? It really does. The pressure acts as a hydraulic fluid, but if it's too thin, we may not be able to properly actuate the VVT solenoid, and that can lead to a delayed or an improper timing adjustment, definitely affecting the engine's performance and its efficiency. Now that's if it's too low. If it's too high, we have consequences there as well. If the oil's too thick, it may resist flow, especially in these colder climate areas or colder conditions, and this can cause the VVT solenoid to respond sluggishly or not at all, resulting in either slowing the timing down or even clogging the solenoid itself. So again, remember, VVT systems rely on precise hydraulic pressure to control the camshaft timing. Now, the solenoids direct oil flow to the camshaft phasers to adjust their position. If that oil viscosity is not within the manufacturer's recommended range, it's going to result in a couple different things that can happen here. You can have erratic timing adjustments where it's inconsistent or unstable, or you can just have increased wear where excessive force may be applied to the solenoids or the actuators when trying to push thicker oil through, which is definitely going to accelerate wear and tear on all those, components. And then we also have to factor in the circulation of contaminants. Remember, we have all these different additives and things that are supposed to trap and contain all those contaminants within the oil and get flushed out when we do an oil change. But when we don't have service intervals being done correctly, we can have a lot of contamination built up within the oil that ends up being deposited. So, the oil viscosity also affects just how many contaminants, such as the sludge or metal particles that are going to move through the system. Now, a higher viscosity oil may trap the particles, while the lower viscosity might actually allow them to circulate more freely. Either way, we don't want this happening. Both situations can lead to a VVT solenoid clogging or just a lot of damage over time. And so you may have noticed when we started, I've got an engine on a stand back here, definitely not a usable engine anymore, and we're going to show you why. We're actually going to zoom in here and show you what it looks like when, one, service intervals are not followed like they should be, but two, what happens to the oil when it's allowed to degrade far past its lifespan and all of those additives just break down. Now, this motor has obviously seen much better days, but this is a great example to show what can happen when service intervals are not followed, oil is allowed to degrade long past its service life, and those additives, those anti-wear, those anti-sludge additives are allowed to break down. Once that happens, we see degradation happen really fast within the oil. We see sludge buildup happen really fast within the oil. And what we have to remember is these solenoids are going to be actuating these phasers. The only way that these solenoids can do their job is if good, clean, cool oil is passing through them. Now, if we look inside here, the oil that we're looking at would be the same oil that's going to try to get past these solenoids. So remember, either too low or too thick, or so say thin or thick oil is going to have a direct impact on whether or not these solenoids can do their job. What we're trying to ask this system to do here is to take this thick, sludgy oil and pass it through these fine, tiny little screens. I'm going to bring this to the bench so you can see a little bit better what I've got. Now, I pulled this out, and it's probably a little bit harder to see from all the way over there, but on part of this screen, it's completely clogged with the same stuff that's on my finger. So again, this system was eventually pulled out of the vehicle, but before that, it was trying to actuate those phasers, getting this oil through these tiny little screens. It's just not going to happen. And the reality is we're going to be replacing solenoids far more than phasers, but in a case like this, we're probably going to have to replace the entire system because now these solenoids can no longer actuate this VVT system the way they were intended to do so. And so again, we could have sluggish riding, we could have, idle issues, we could have check engine lights. In this case, we're probably not going to have the car start at all. But the point I'm trying to make here is when we allow that oil to degrade and those additives to fall apart like they're going to do anyway, they're going to eventually degrade and wear out, but they're supposed to, along with that service life. So if the vehicle says, you need an oil change at 5,000 miles, that means it knows that the oil that's going in there should maintain and protect that motor for that 5,000 miles, and the additives within should also degrade gradually along with the oil so that we don't have this kind of thing building up on the solenoids or internally in the valve train. Once we see this, it's pretty much a no-go. We're going to have a lot of issues, probably going to have to replace the motor, but best case scenario, all new solenoids, phasers, and probably an entire timing setup if we haven't caused further damage in the timing as it is. So this is just a good example of what happens when we allow oil to degrade. Again, we've got to get it through these fine metal screens. It's not going to happen when it's thick and sludgy like this. What we should be looking for, and I've got on a card over here, is a good clean passage, and I'll show you what that looks like. Now, obviously in this example, we have a head that's been pulled off that is in much better condition than the one we just looked at, and it was probably pretty well maintained. Surely we've cleaned it up quite a little bit here, but we would not expect to see this level of cleanliness had it been allowed to degrade the oil and go well past its service life multiple times over. So, but this is a good example of what we should see when we pull a valve cover off, aside from the fact that it's not lubricated at all here. The thing I want to point out though is, we just saw an example where the solenoids are, pretty clogged, and it's going to be really hard to get that oil through the solenoid, but we have to think about the channels before even the solenoid. How does the oil get to those solenoids? Well, we have very small channels for this oil to get its way into the solenoid and then onto the phaser. So again, if we're thinking about the engine from before with all that sludge buildup, In some cases, we may not have to worry about destroying the solenoid because the oil may not even be able to make it through these fine little tiny passages to get to the solenoid. So we have to think about it in a couple of different ways. We got to make sure that the solenoid can pass the oil through the screen, but we also have to make sure that the oil can even make it to the solenoid. So again, the minute we start clogging up these small little channels for the oil to get to the solenoids, we already have a problem. If we continue trying to force the issue and push it through, we're going to destroy the solenoids at the same time. So why does cool oil matter? Well, in the case of VVT, it allows those different additives to stay viable through the service life so that it can work its way through the system and up through these small little tiny channels to make its way to the solenoid so that our phasers can be actuated properly. All right, so now we've talked a little bit about what the oil is supposed to do, what we hope it's supposed to do, all the tasks that it has to complete. We've talked about what they put in the oil that helps it do those things. There's a lot of things that it's supposed to do. Those additives are what help it do those things. And then we've talked about some of the systems that are critically dependent on good clean oil, but also cool oil. So we know those systems, we know what it's supposed to do, we know how it's supposed to do it. So what do optimal temperatures look like? When we say, why does cool oil matter? Well, what does cool oil look like? Well, let's talk about that. Let's talk about the optimal temperature ranges and why they are. In most automotive engine applications, the temperature of the engine oil is going to range, on average, between about 180 degrees and 220 degrees Fahrenheit. Why is this the optimal range? Why is this the sweet spot? Well, most modern engines are going to be designed to operate efficiently when the oil temperature is within that range. Now, at these temperatures, the oil can maintain not only the right viscosity to provide the lubrication that's required, but also reduce friction and protect the engine components. But just as importantly, and this is very important, this is also the temperature range that most of the additives are designed to withstand throughout the life of that oil change. Meaning rapid breakdown should not occur, and everything we've talked about so far will be taking place as the oil is able to function as designed and formulated for that vehicle's needs. And so when we ask the question, why does cool oil matter? Well, we've talked about a lot of reasons why it matters, but I really think we should break it down to those additives. Those additives are meant to withstand 180 to 220 for the intended service life of that oil. As those additives start to degrade, we're not protecting the motor anymore. We're not cleaning the motor anymore. We might be losing pressure. There's a lot of things that can build up, deposits, carbon, things like that within the motor because we're not pulling those contaminants away. So the idea here is if we can keep the oil cool, it's going to lubricate the engine better, but it's going to maintain those additives within the oil so that they can protect the engine throughout the service life of that oil change. Now, keep in mind, all of these additives are going to degrade, right? They're going to degrade along with the service life of the oil. But if we have an application, let's say 180 to 220 is the optimal range. We know that. But let's say we're doing a lot of hauling and a lot of towing or something like that where the temperatures are exceeding that range frequently. Well, we need to consider possibly doing quicker oil changes. If the recommended is, say, 5,000, we might want to bring it down to 3,000, 3,500, because with excessive heat, we're going to degrade those additives much faster. We're not going to be able to protect the engine the way that we should. So why does cool oil matter? Well, it matters because the overall protection of the engine really comes down to not only the viscosity of the oil, its ability to lubricate, but the enhancement of all those additives being able to do their job. And obviously the way we accomplish this, keeping the oil cool, is through a process of using oil coolers. Now, whether it's a complete housing, standalone cooler and gaskets, domestic or import, most modern vehicles are going to require an oil cooler for a multitude of reasons. Now, the oil cooler plays a crucial role in regulating the overall temperature of the oil in the average automotive engine. And, there's a lot of things that it does, but here's how it impacts oil temperature during operation. It's going to prevent the oil from overheating. And its function is fairly simple. The oil cooler acts as a heat exchanger. It's going to transfer heat from the hot oil to the surrounding air or the coolant. And with doing so, the impact is that it's going to prevent the oil from reaching excessively high temperatures, especially when we're doing things like towing, hauling, even racing, or driving in much hotter or higher temperature climates. It's also going to maintain oil temperature. So remember, the oil cooler is going to help keep the oil temperature within that optimal range of 180 to 220 degrees Fahrenheit, which is going to help ensure that the oil remains effective at lubricating, cleaning, and cooling the engine components. It's also going to reduce oil degradation. Remember, when the oil temperature rises above really anything above 250 for extended periods of time, the oil can and will degrade at a much faster rate, along with the additives we talked about, meaning it's going to lose its ability to lubricate and protect effectively. And so by cooling the oil, the cooler extends its life and maintains its viscosity. It also is going to improve engine performance and longevity. By maintaining stable and consistent oil temperatures, the oil cooler is actually going to help the engine perform efficiently and reduce wear and tear on a lot of the critical components. There's also an added benefit to this of thermal stress reduction. Consistently cool oil is also going to prevent thermal stress on engine parts that occurs due to uneven or excessive heating. It's also going to enhance heat dissipation. Remember, engine oil absorbs heat from friction and combustion. So the oil cooler dissipates that heat, reducing the overall thermal load on the engine and basically kind of like supplementing the radiator's cooling system. Now, there are some limitations in, say, like very cold climates or very cold conditions. So we do have some modern systems out there that include a thermostat to bypass the oil cooler when the oil is too cold, essentially allowing the oil to just bypass the oil cooler. It's going to allow us to get a startup. It's going to allow the oil to start lubricating the system. And then when we get a little bit of heat built up, it'll go ahead and shut off and allow the oil to go back through the oil cooler and complete its rounds throughout the rest of the drive cycle. So now we know what the oil cooler is supposed to do. So the question is, how does the oil cooler work? Well, it's going to vary from style to style. Now we have some that are going to be made from aluminum, even sometimes copper. And really the main part of the oil cooler is going to resemble somewhat of like a mini radiator or a condenser. These are going to have a series of thin metal fins and tubes inside of them. And the oil is going to flow through the network of those small tubes inside the cooler, and the tubes are often going to be corrugated as well, or finned internally to increase that turbulence, which is going to enhance the heat transfer by keeping the oil moving efficiently. Now, in other cases where we have a lack of airflow, they could be made from a high-strength synthetic material like Zytel, and that's when they're going to be mounted in locations where air just doesn't pass through or over. Now, with this style, we'll find a similar style aluminum cooler on top that's exchanging the heat. The housing itself is going to be designed to withstand the extreme heat where it's located, making it possible to dissipate that heat passing through it and being exchanged through the cooler itself. And the cooler essentially has two sets of ports. It has an inlet and an outlet for the hot oil to come in from the engine, be cooled, and then returned through the system. Now, the way they're designed to flow can vary a couple different ways. Some oil coolers will just use a parallel flow system with multiple tubes in parallel for even cooling, while we may have others use a serpentine flow with oil moving in more of a zigzag pattern through a single path for maximum heat transfer. And there's also various cooling methods. Now, they can just be air-cooled, where really they're just simply mounted in a location where airflow passes through it, so like near the radiator or near the grill. Now, they can also be liquid-cooled, using coolant instead of just the air to absorb the heat, really integrating the oil cooler with the engine's cooling system itself. And some use both methods simultaneously, depending on the location where it's mounted. And so if I zoom in here, I can actually show you an example of one of those coolers that does use both versions simultaneously, where we're going to actually have air cooling and liquid cooling, because this unit's going to be mounted in a location where it does actually receive some supplemental airflow to help cool things down. But primarily, we're going to be using the engine's coolant system with an inlet and an outlet so that some of the channels within this cooler can have that coolant running through it, doing the heat exchanging, and then the other channels are where the oil is going to pass through, receiving that heat exchange. So we have our inlet and outlet of coolant coming in, then we have our oil actually coming in from the engine side through this tube. Then it's going to work its way back out into the oil filter. Here's where our oil filter will be mounted. So the oil comes through hot, it gets filtered through the oil, and then it's going to work its way through to this channel right here above at the top where the oil filter is mounted. And that's where the oil is going to find its way into the cooler, go through its channels, and be rapidly cooled by those channels of coolant running through them. And then it's going to exit out of the back and back into the system cooler than it was coming through, effectively, again, helping us transfer that heat that the oil has picked up from all those moving components that it's been crossing over and washing over throughout the drive cycle. So knowing how these work, it's pretty easy to see that much like the VVT solenoids or turbochargers, there are a lot of systems dependent not only on the oil cooler doing its job and keeping the oil cool, but the oil not degrading far past what it's supposed to, because then we end up with that sludgy film that we see on the motor behind me. Remember, if we're trying to push that through the screens of the solenoid, it's not going to happen. It's also going to be pretty impossible to get that sludge through the oil cooler so that it can be cooled down. And what's going to end up happening is, just like those VVT solenoids, if we allow the oil to degrade far past its intended lifespan, even if the oil cooler is doing its job, that oil is going to break down, and then we're going to end up clogging up the oil cooler just like we would the VVT solenoid. So it's important, again, not only for the oil to be cool, but the oil to be changed at the right intervals so that the oil cooler can do its job. And with that, we also have to talk about the cooling system. So some of these, again, are air-cooled and cooled through the cooling system of the vehicle. And so we have to consider the quality of the cooling system as well. And for that, we'll go to the trusty 6.0 diesel Ford Power Stroke oil cooler to give you a couple of examples of what can happen when we have not only oil degradation, but coolant degradation and the overall system not working properly. So again, in addition to clogging from a poor lack of maintenance, the overall cooling system of the vehicle is going to have a large impact on the oil cooler's ability to effectively do its job. And so with these style of coolers, we have to remember, we have to consider maintenance on two fronts, right? We have to look around the same issue, and that is from restrictions on either clogged oil or clogged coolant. In either case, the cooler's ability to do its job, really rapidly dissipate heat, can and will be dramatically affected by that poor maintenance, and it's ultimately going to lead to a failure. Now, for those of us out here who have worked on 6-liter Power Strokes more than we care to admit, we know that with the oil cooler on these systems, there are some symptoms we can find pretty quickly if we know that we've had overheating issues or we've got a complaint of overheating. Sometimes all we have to do is pull the oil filter and look at the standpipe for the oil filter. Is it still intact? If we've overheated, oftentimes it's going to be melted, and now we know we've got an issue, a restriction somewhere. Something is causing this system to overheat. Is it going to be in the coolant? Is it going to be in the oil? Or is it going to be a combination of both? But just a quick tip here. If you find this, we know we've got an overheating issue. So now the question is it a restriction? Well, restricted oil cooler can be the result of overheating, obviously, or a damaged oil filter. And another tip here is if the EGR cooler is plugged on these systems, the oil cooler is probably going to be plugged as well. And a good way to check for that restriction, obviously, let's test drive the truck. Let's get it nice and hot. And let's compare the engine coolant temperature to the engine oil temperature. There is a TSB on this, TSB 08-11-3, gives you a little bit more details on this. But what it's stating is that the engine oil temperature should be about 225 when the engine coolant temperature is around 200 degrees Fahrenheit. So if there's more than a 25 degree spread during, the diagnosis or checking on the concern, the chance is we're probably going to have to replace the oil cooler because there's probably a restriction. The reason I bring this particular example up is there are going to be in service information a lot of vehicles where we can find information about what the variation should be. Should it be 225 at around 200 or should it be 175 at 210? It just depends on the vehicle, but I would, highly encourage you to look at service information for this type of, data so that if you are trying to diagnose whether an oil cooler is restricted or not without having to tear the entire system apart, maybe we can find something in that service information that gives us a range to look at before we start disassembly. And so in summary, why cool oil matters is pretty simple. It protects the motor and it helps pull heat away from those critical components. It also allows the viscosity and protection of those additives to withstand the intended service life of the oil. And because of oil coolers, along with routine maintenance, the oil can effectively do its job to contain all those harmful deposits that will otherwise damage critical systems like turbochargers and those variable valve timing components. So basically, the cooler the oil, the longer the motor will last and run efficiently throughout its lifespan. And before we go, don't forget, we do have some additional resources available to you. If you go to YouTube, you can look up Standard Brand, where we have hundreds of videos, things like installations, tech tips. We also have all of the previous power hours from last year and the beginning of this year on our YouTube channel there. We also have standardbrand.com, where you can go on and find our entire e-catalog, every part, images of those parts, and various information that goes along with those. Sometimes even installation tips and full installation guides, as well as a lot of content, like in this example, the oil filter housing kits, gives you a breakdown of exactly how they're made, what they're made with, and maybe some solutions that might help you in the future. All right, well, hey, again, in the spirit of time, I know I've gone over a little bit, but I want to thank everybody for being here, and hopefully this will give you a little bit better understanding of why it's so important to keep the engine oil cool in your car today. Till next time, thanks for being here. We'll see you soon.